A single steel edge, sharper at its tip than any cell is wide, slides through the surface of your skin and severs roughly 10,000 cells in the space of a heartbeat. It cuts capillaries no wider than a red blood cell. It tears the scaffolding that held your tissue together. And before the pain signal has even finished traveling up your arm to your brain, before you have looked down to see what happened, a repair operation older than your species has already begun. Within seconds, platelets, tiny fragments of cells with no nucleus and no DNA, are tumbling out of the broken vessel, touching the exposed collagen at the wound edge and changing shape. They flatten. They grow sticky arms. They release the contents of their internal storage granules into the wound. And they begin, without a single instruction from your conscious mind, to build a dam. That dam is a blood clot. It is one of the fastest and most elegant emergency responses the body performs. A cascade of proteins floating in your blood, more than a dozen of them, each one activating the next like a row of falling dominoes, converts a soluble protein called fibrinogen into long, sticky threads of fibrin. Those threads weave themselves into a mesh across the wound, trapping platelets and red cells, sealing the breach. The whole sequence, from cut to clot, can finish in 3 to 5 minutes. And here is the part that matters for everything that follows. That clot is not just a plug, it is a scaffold and a signal. Packed inside the platelets that built it are growth factors, molecular messages with names like platelet-derived growth factor and transforming growth factor beta, and as the platelets break open, those messages flood into the wound and call for the next crew to report for duty. The clot is a construction site posting a help wanted sign written in chemistry. When you were 8 years old and you scraped your knee on the pavement, this entire system ran at full speed. You did not notice. You wiped off the blood, maybe cried for a minute, and by the next morning a scab had formed. Within 3 or 4 days the scab tightened and itched. Within a week it fell off, and underneath was new skin, slightly pink, perfectly closed. You did not think about platelets or fibrin or growth factors. You did not need to. The repair crew was young, fast, and fully staffed, and it did its work while you slept and ran and forgot the injury entirely. That is the experience nearly everyone carries from childhood. The quiet assumption that skin simply closes itself, that a wound is a temporary thing the body erases on its own. Now you are past 50, and you have noticed something. A cut on the back of your hand that would have vanished in a week now takes 3. A scrape lingers, stays red, scabs and rescabs. A blister on your heel that should have been gone by Friday is still there the following Wednesday. You are not imagining it. The repair crew is still there. The same platelets, the same fibrin, the same growth factors, the same ancient cascade. But the crew has aged along with you, and the slowdown you are seeing is not laziness and it is not bad luck. It is physics and chemistry operating on cells that have lived a long time, and once you understand what is actually happening inside that wound, the delay stops being mysterious and becomes something you can do something about. Here is the first mechanism. Once the clot has formed and the help-wanted signal has gone out, the most important workers in the rebuilding phase begin migrating into the wound. They are called fibroblasts. A fibroblast is a spindle-shaped cell that lives in the dermis, the layer beneath your skin's surface, and its job is to manufacture the structural material that holds your body together. That material is collagen, the most abundant protein in your entire body, making up roughly 1/3 of all the protein you contain. Collagen is rope, it is rebar, it is the cabling and scaffolding that gives skin its strength and tissue its shape. When you are wounded, fibroblasts crawl into the gap, anchor themselves to the fibrin mesh, and start spinning out new collagen, molecule by molecule, weaving a fresh matrix to replace what the blade destroyed. They also contract, physically pulling the wound edges closer together, shrinking the gap they have to fill. A young, healthy fibroblast is a tireless little factory, dividing when more workers are needed, secreting collagen at high speed, responding instantly to the growth factor signals in the wound. And this is exactly where age changes the equation. Your fibroblasts, like nearly every cell in your body, cannot divide forever. In 1961, a scientist named Leonard Hayflick made a discovery that overturned what biologists believed at the time. The prevailing assumption was that cells, given the right nutrients, could divide endlessly. Hayflick took human fibroblasts, the very cells that rebuild your wounds, and grew them in the laboratory, and he found something nobody expected. They divided about 50 times, and then they stopped. Not because they died, not because they ran out of food, but because they reached a built-in limit. They entered a state we now call senescence, still alive, still metabolizing, but no longer able to divide. This number, roughly 50 divisions for human fibroblasts, became known as the Hayflick limit, and it pointed to something profound. Cells count. They keep track of how many times they have divided, and they have a ceiling. The mechanism behind that counting was discovered decades later, and it earned a Nobel Prize in 2009 for Elizabeth Blackburn, Carol Greider, and Jack Szostak. At the very ends of each of your chromosomes sit protective caps called telomeres. Think of them as the hard plastic tips on the ends of a shoelace, the aglets, that keep the lace from fraying. Every time a cell divides and copies its DNA, the copying machinery cannot quite reach the very end of the strand, and a small piece of telomere is lost. 50 to 200 base pairs of genetic sequence trimmed away with each division. The telomere is a buffer, a length of expendable DNA that protects the real genes inside from being shaved off. But the buffer is finite. After enough divisions, the telomere grows critically short, and the cell receives a signal, an alarm that says the protective cap is nearly gone, and dividing again risks damaging the actual genome. So, the cell stops. It goes into senescence, and here is the connection to the wound on the back of your hand. By the time you are past 50, a significant fraction of the fibroblasts in your skin have already used up most of their divisions across decades of ordinary tissue turnover. Their telomeres are short. When a wound calls for a fresh wave of dividing fibroblasts to crawl in and build collagen, the response is slower and the numbers are smaller, because more of the available cells have hit their limit and can no longer multiply on demand. But the slowdown is not only about how many fibroblasts you can muster, it is also about how hard each one works. Studies of skin biopsies have shown that fibroblasts from older adults synthesize less collagen than fibroblasts from young adults, even when they are dividing. The factory runs at reduced output. Across the adult lifespan, the skin loses collagen at a rate of roughly 1% per year, and the older fibroblasts not only build less new collagen, they also produce more of a class of enzymes called matrix metalloproteinases, molecular scissors, whose job is to cut and break down collagen. In a young wound, building outpaces breaking by a wide margin, and the matrix fills in quickly. In an older wound, the balance tilts. Construction slows, demolition rises, and the net result is a wound that takes longer to fill the gap with strong, organized tissue. The scaffolding goes up more slowly, and it is thinner when it is finished. There is a structural change in older skin that makes all of this worse, and you can almost feel it if you pinch the skin on the back of an older hand and watch how slowly it settles back. Young skin has a wavy, interlocked border between its top layer, the epidermis, and the layer beneath, the dermis. Those interlocking ridges, called rete ridges, are like the teeth of two combs pressed together, and they do two things. They lock the layers tightly so the skin resists shearing, and they create niches where stem cells live, the reserve population that supplies fresh cells for repair. With age, those ridges flatten. The border between the layers becomes smooth. The two combs pull apart. This means the skin tears more easily under small forces, which is why older skin bruises and abrades from minor bumps that would never have marked it at 25, and it means there are fewer protected niches holding the stem cells that wound healing draws upon. The epidermis itself grows thinner. The cells that resurface a wound, the keratinocytes, migrate more slowly across the gap, and the whole timeline of closing a wound stretches out. The construction crew is smaller, slower, builds less per worker, and tears down more, all on a job site whose underlying structure has weakened. None of this is failure. It is the predictable arithmetic of cells that have lived for decades, counting their divisions, spending their telomeres, doing exactly what their chemistry dictates. Before the construction crew can rebuild, another crew has to do the dirty, dangerous work first. And to understand why your wounds heal slower after 50, you have to follow what happens in the hours and days right after the clot forms. A wound is not a clean event. The blade that cut you dragged bacteria from the surface of your skin down into the tissue. The dead and dying cells at the wound edge are leaking their contents. There is debris everywhere, torn fragments of membrane, spilled proteins, broken scaffolding, and there are microbes that, given a few hours of warmth and moisture and free nutrients, would multiply into an infection that could spread. Something has to go in first and clean. Something has to kill the invaders and clear the wreckage before the fibroblasts can lay down fresh collagen on solid ground. That something is your immune system, and the first wave it sends is one of the most aggressive cell populations your body owns. Within minutes to a few hours of the injury, the growth factors and distress signals pouring out of the wound reach the nearest blood vessels and pry them open at the cellular level. The cells lining those vessels loosen their connections, the vessel walls become leaky, and through the gaps come the neutrophils. A neutrophil is a white blood cell, a first responder built for one purpose: to find and destroy invaders fast. They arrive in enormous numbers, and they are brutal. A neutrophil engulfs bacteria whole, swallowing them into internal compartments where it douses them with a chemical arsenal, bursts of reactive oxygen, hydrogen peroxide, bleach-like compounds, enzymes that dissolve cell walls. Some neutrophils go further and explode on purpose, flinging out webs of their own DNA studded with toxic proteins, nets that trap and kill bacteria in the open. This is total war conducted at the scale of single cells, and in a young wound, it is over quickly. The neutrophils flood in, they sterilize the battlefield, and then, crucially, they die and are cleared away. Their lifespan is short, only a day or so, and that brevity is by design. You do not want this much firepower sitting in your tissue any longer than necessary, because the same chemical weapons that kill bacteria also damage your own cells. After the neutrophils comes the second wave, and this crew is the true conductor of the whole repair operation. They are called macrophages, a word that literally means big eaters, and they arrive a day or two after the injury. Macrophages are larger, longer-lived, and far more sophisticated than neutrophils. They finish the cleanup, devouring bacteria, swallowing the spent neutrophils, digesting the debris, clearing the dead tissue. But their most important job is what they do next, and it is one of the most elegant transitions in all of physiology. The macrophage changes its personality. In the early phase, it is in attack mode, an inflammatory cell pumping out alarm signals, recruiting more immune cells, keeping the battle hot. Scientists call this the M1 state. Then, as the wound is cleaned and the threat recedes, the macrophage switches. It transitions to what is called the M2 state, a repair and rebuild mode, and now instead of shouting alarms, it begins releasing the growth factors that tell fibroblasts to come in and build collagen, that tell new blood vessels to grow, that tell the inflammation to wind down. This switch, from M1 to M2, from demolition to construction, from inflammation to resolution, is the hinge on which the entire healing process turns. When it happens cleanly and on schedule, the wound moves smoothly from the cleanup phase into the rebuilding phase. When it stalls, the wound gets stuck. And here is where age changes everything. Your immune system ages too, and scientists have a name for it: immunosenescence, the gradual decline in the function and coordination of your immune cells over the decades. In an aging body, the neutrophils that arrive at the wound are less precise. Studies have shown that neutrophils from older adults are worse at the targeted hunting and killing of bacteria, their internal navigation degraded, so they wander and miss their targets, yet they still release their chemical weapons. The result is the worst of both worlds. The bacteria are cleared less efficiently, raising infection risk, while the collateral damage from misfired toxic chemicals rises, harming the very tissue that is trying to heal. The first responders show up, but their aim is off, and the wound pays for it. The macrophages have an even bigger problem, and it sits at the heart of why older wounds stall. That critical switch from attack mode to repair mode, from M1 to M2, becomes sluggish and unreliable with age. The aging macrophage tends to get stuck in the inflammatory state. It keeps shouting the alarm long after the threat is gone. It delays the transition to the rebuild signals that the fibroblasts and blood vessels are waiting for. So the wound sits in a prolonged inflammatory phase, full of cells that are still acting as if there is a battle to fight, when what is actually needed is construction. The help wanted sign for the building crew goes up late, and the building crew, as we saw, was already smaller and slower to begin with. The two delays compound. The cleanup crew will not leave, and the construction crew cannot start. Underneath this lies a phenomenon that researchers have come to see as one of the central features of aging itself, and it has been given a name that captures it perfectly: inflammaging, a blend of inflammation and aging. As you grow older, your body settles into a state of chronic, low-grade, smoldering inflammation throughout your tissues, even when there is no injury and no infection. The levels of inflammatory signaling molecules circulating in your blood, proteins with names like interleukin-6 and tumor necrosis factor alpha and C-reactive protein, drift steadily upward across the decades. This is not the sharp, useful, short-lived inflammation of a fresh wound that flares and then resolves. It is a constant background hum, a fire that never fully goes out. And one of the major sources of that fire takes us straight back to the senescent cells from the construction crew, the fibroblasts that hit their Hayflick limit and stop dividing. Those senescent cells do not simply go quiet. They begin secreting a cocktail of inflammatory molecules, a phenomenon researchers call the senescence-associated secretory phenotype. A senescent cell is a cell that can no longer divide but refuses to die, and it sits in your tissue, leaking inflammatory signals into its surroundings, year after year. The more of these cells you accumulate, and you accumulate more every year, the higher your baseline inflammation climbs. Now put a fresh wound into a body that is already simmering with chronic inflammation, and you can see the trap. The wound needs a clean, sharp pulse of inflammation that rises fast to fight infection, and then resolves fast so that rebuilding can begin. But the aging body cannot deliver a clean pulse because it is already inflamed at baseline, and the macrophages that should orchestrate the resolution are themselves impaired and stuck in attack mode. So, instead of a sharp spike that falls back to zero, the wound's inflammation rises and then plateaus, lingering, refusing to resolve. The wound becomes a place where the cleanup crew sets up permanent residence, continuously releasing the molecular scissors, the matrix metalloproteinases that chew up collagen, so that even the small amount of new matrix the older fibroblasts manage to build is partly destroyed as fast as it goes up. This is the biological reality behind a wound that stays red, stays open, scabs and rescabs and will not close. It is a wound trapped in the inflammatory phase, unable to make the transition to repair. This is also why chronic wounds, the kind that genuinely do not heal for months, are overwhelmingly a condition of older bodies. A diabetic foot ulcer, a pressure sore, a venous leg ulcer, these are wounds that have become permanently locked in the inflammatory state. The macrophages never switch. The inflammation never resolves. The tissue sits in a self-perpetuating cycle where inflammation damages tissue, and the damaged tissue triggers more inflammation, and the loop feeds itself indefinitely. These wounds are a leading cause of disability and amputation in older adults, and at the cellular level, they are the extreme end of the same process that makes an ordinary cut on the back of your hand take 3 weeks instead of 1. The difference between a slow wound and a chronic wound is a matter of degree. The same stuck switch, the same lingering inflammation, the same imbalance between building and breaking pushed further. There is one more layer to this, and it connects the cleanup crew to a system you might not associate with skin at all: your lymphatic vessels. Alongside your blood vessels runs a second network of thin-walled channels that drain excess fluid out of your tissues and carry immune cells back and forth, and this lymphatic drainage is part of how a wound clears the byproducts of inflammation and resolves the swelling. With age, the lymphatic vessels become less efficient, their walls stiffer, their pumping weaker. Fluid that should be drained away lingers in the tissue around the wound, and that lingering fluid, swollen and stagnant, further slows the delivery of oxygen and the clearance of waste, adding yet another break to a process already running behind. The swelling that takes longer to go down around an older injury is part of this same picture, a drainage system that has slowed along with everything else. Stand back and look at what the cleanup crew has become. The neutrophils still come, but their aim has drifted, killing less efficiently while damaging more. The macrophages still come, but they get stuck in attack mode and delay the switch to repair. The whole body is already simmering in low-grade inflammation, stoked by senescent cells that will not die and will not stop leaking alarm signals. The drainage that should clear the swelling has slowed. And so the wound that needed a quick, clean burst of inflammation, followed by a fast handoff to the builders, instead gets a long, smoldering, unresolved inflammatory state that chews up new collagen as fast as it forms. The cleanup crew, in a young body, was a disciplined strike team that came, conquered, and left on schedule. In an older body, it is a crew that arrives a little disorganized, fights a little sloppily, and then refuses to go home. That refusal, more than almost anything else, is why your wounds heal slower after 50. But there is still one more system we have not followed, and it may be the most important of all, because without it, neither crew can do its job at all. It is the supply line, and that is where we go next. Every crew we have followed so far, the construction workers laying down collagen and the cleanup teams fighting infection, shares one absolute dependency, and it is so fundamental that we tend to forget it is even there. They need supplies. They need oxygen to burn for energy. They need amino acids to build collagen out of. They need glucose for fuel, and they need a way to haul away the waste they generate. All of that arrives through one delivery system, your blood vessels, and a wound presents that system with a serious problem. The blade that cut you severed the local capillaries. The very vessels that fed the tissue are now broken and clotted off. The cells trying to rebuild the wound are working in a zone where the supply lines have been cut, and if those lines are not restored quickly, nothing else can proceed, no matter how willing the workers are. So the body does something remarkable. It grows brand new blood vessels on demand directly into the wound. This process is called angiogenesis, the birth of new blood vessels, and it is one of the most impressive feats of construction the body performs. Here is how it works. The cells in the center of the wound, cut off from their blood supply, are starving for oxygen, and that oxygen shortage is not just a problem, it is a signal. Low oxygen, a state called hypoxia, switches on a master regulator inside the cells, a protein with the unwieldy name hypoxia-inducible factor. When oxygen is plentiful, this protein is destroyed almost as fast as it is made. When oxygen runs low, it stops being destroyed, it accumulates, and it travels to the cell's DNA and switches on a set of genes, the most important of which produces a signaling molecule called vascular endothelial growth factor, VEGF for short. VEGF is a chemical cry for help that means, in effect, we are suffocating in here, send blood. It diffuses out from the oxygen-starved wound and reaches the nearest intact blood vessels, and the cells lining those vessels respond. They begin to sprout. One cell at the tip leads the way, crawling toward the source of the VEGF signal toward the hypoxic center, and the cells behind it follow and organize themselves into a hollow tube. A new capillary grows, sprouting like a root toward water, reaching into the wound, and when it connects with another sprout, blood begins to flow through the new channel. The wound, formerly a dead zone, is reconnected to the supply network. The tissue that grows in to fill a wound, that red, slightly bumpy, intensely vascular tissue a surgeon calls granulation tissue, is named for its grainy appearance, and those grains are the tips of thousands of brand new blood vessels packing the wound with fresh supply lines. A healthy wound becomes one of the most densely vascularized tissues in the body, temporarily, precisely because the demand for oxygen and materials is so high. And now you can probably guess where age intervenes, because it intervenes here too, and the consequences ripple through everything. Angiogenesis slows down with age. The cells that line your blood vessels become less responsive to the VEGF signal. The signal itself may be produced in lower amounts or less efficiently. The new vessels that do form grow more slowly, are sparser, and are sometimes more fragile and disorganized than the dense, robust network a young wound generates. This means the wound takes longer to restore its blood supply, and until that supply is restored, the whole repair operation runs starved. But the age-related slowing of angiogenesis is only the beginning of the supply problem, because the pipes that the new vessels have to connect to, the larger arteries and arterioles that feed the region, have themselves changed over the decades, and those changes restrict flow before the blood ever reaches the wound. Consider what happens to arteries with age. The walls of your arteries stiffen, a process driven in part by the same collagen chemistry we have been discussing, plus the accumulation of calcium and the cross-linking of proteins that makes tissue rigid. A young artery is elastic, expanding with each heartbeat and recoiling to keep blood moving smoothly. A stiffened artery cannot do this as well, and blood flow to the periphery, to the skin of your hands and feet and legs where wounds so often occur, becomes less responsive and less abundant. Layer onto this the conditions that grow more common with each passing decade: atherosclerosis, the buildup of plaque that narrows the arterial channel; hypertension, which damages the small vessels over time; and above all, diabetes, which is perhaps the single most powerful accelerator of wound healing failure known to medicine. Chronically elevated blood sugar damages the small blood vessels throughout the body, thickening their walls, narrowing their channels, and crippling the microcirculation, the network of the tiniest vessels that actually delivers oxygen to individual cells. Diabetes also damages nerves, so that a person may not even feel a wound forming on the foot, and it impairs immune cell function on top of everything else. This is why a diabetic foot ulcer is so dangerous and so stubborn. It is a wound trying to heal in tissue whose supply lines have been narrowed at every level, from the large arteries down to the smallest capillaries. While the repair crews are simultaneously impaired, it is the convergence of every problem we have discussed concentrated in one place. There is a molecule that ties the supply problem to one of the mechanisms we have touched on, and it deserves a moment because it explains why circulation in older tissue is restricted in a way that goes beyond simple plumbing. The cells lining your blood vessels produce a gas called nitric oxide, and that gas is the signal that tells the smooth muscle wrapped around your arteries to relax, widening the vessel and increasing blood flow. Nitric oxide is how your body opens the supply lines on demand, dilating vessels where more flow is needed. With age, and especially with the chronic inflammation we discussed, the cells lining your vessels produce less nitric oxide and respond to it less well. The reactive oxygen molecules that flood an inflamed, aging body actually destroy nitric oxide directly, mopping it up before it can do its job. So the aging, inflamed body has a reduced ability to dilate its own vessels and increase flow to a wound that is crying out for more oxygen. The supply lines are not just narrower, they are also harder to open. This connects directly back to the cleanup crew, because the chronic inflammation of inflammaging, with its flood of reactive oxygen, is part of what suppresses the nitric oxide that the wound needs to widen its vessels. The systems are not separate. The inflammation that will not resolve is also strangling the blood supply that the resolution depends on. And here is the cruelest part of the loop, the place where the whole story closes back on itself. Remember the construction crew, the fibroblasts building collagen. Building collagen is not a passive process. It requires oxygen as a literal chemical ingredient. The collagen molecule must be chemically modified to become stable and strong. A step called hydroxylation, in which specific amino acids in the collagen chain have oxygen atoms attached to them, and this step is performed by enzymes that cannot function without oxygen and vitamin C as their cofactor. Without enough oxygen, the collagen that fibroblasts produce is weak, unstable, and falls apart. So, oxygen is not just fuel for the workers, it is raw material for the product. Now follow the loop. The wound needs oxygen to build collagen. To get oxygen, it needs blood vessels. To grow blood vessels, it needs angiogenesis. Angiogenesis is slowed by age, and the existing vessels are narrowed by stiffening and disease, and starved of the nitric oxide that would open them. So, the wound cannot get enough oxygen, which means it cannot build strong collagen, which means the tissue stays weak, which means it is more easily re-injured and slower to close, while the low oxygen and chronic inflammation keep the cleanup crew agitated and stuck, which keeps the inflammation high, which keeps destroying the nitric oxide and chewing up what little collagen does form. Every system we have followed feeds into every other. The slow construction crew, the stuck cleanup crew, and the narrowed supply lines are not three separate problems. They are one problem viewed from three angles, a single web of interlocking delays, and that is the honest, physical reason. A wound that closed in a week at 25 takes a month at 65. Now, honesty requires a pause here, the same kind of pause that any complete account demands, because it would be easy to leave you thinking all of this is simply inevitable decline, And that is not the truth either. Some of what we have described is genuinely unavoidable. You cannot reset your telomeres. You cannot reverse the Hayflick limit. You cannot make your fibroblasts young again, and you cannot undo the flattening of the reed ridges or the decades of divisions your cells have already spent. The baseline slowing of wound healing with age is real, it is measurable, and no cream or supplement or routine will return your skin to the repair speed of childhood. Anyone who promises that is selling something. But, and this is the part that matters, a very large fraction of the difference between a wound that heals at a reasonable pace and one that drags on for months is not the unavoidable cellular aging at all. It is the modifiable layer sitting on top of it, the layer you actually have leverage over, and understanding the mechanisms is exactly what tells you where that leverage is. Start with the supply lines, because that is where the leverage is greatest. Everything that improves your circulation improves your wound healing directly through the mechanisms we just traced. Movement, walking, using your muscles, drives blood through your vessels and stimulates the production of nitric oxide by the cells lining them, the very molecule that dilates vessels and opens the supply lines. A body that moves maintains better microcirculation than a body that sits, and the difference shows up at the wound. Not smoking, or quitting if you do, is among the most powerful single things within your control, because the chemicals in tobacco smoke constrict your blood vessels, poison the oxygen-carrying capacity of your blood, and damage the vessel lining directly, choking off the supply to every wound in your body. A smoker's wound heals dramatically slower than a non-smoker's, and that gap closes when the smoking stops. Managing blood sugar, whether you are diabetic or merely drifting toward it, protects the microcirculation and the immune function that diabetes so badly degrades, and it is arguably the most important medical lever of all for anyone whose blood sugar runs high. Controlling blood pressure protects the small vessels. Every one of these acts on the supply line mechanism we just described, and the supply line is the bottleneck through which everything else must pass. Then there is the raw material the construction crew cannot build without. Collagen is a protein, and an aging body that does not eat enough protein simply cannot supply its fibroblasts with the amino acids to make it, and protein deficiency in older adults is far more common than most people realize, especially in those eating less and cooking less. Adequate protein is not optional for wound repair, it is the substrate. Vitamin C is the essential cofactor for the enzyme that stabilizes collagen, the very hydroxylation step that requires oxygen, and a deficiency leaves collagen weak and falling apart, which is why scurvy, in its full historical form, was a disease of wounds that reopened and would not heal. Zinc is required for the enzymes of cell division and immune function, and deficiency slows everything. None of these are exotic, none are expensive, and all of them are more often lacking in older bodies than in young ones, which means correcting them can recover a meaningful share of the lost healing speed, not because they are magic, but because they remove a brake that was needlessly applied. And the cleanup crew, the inflammation that will not resolve, responds to the same broad levers, because chronic low-grade inflammation, inflammaging, is influenced by the things that influence your whole metabolic state. Excess body fat, particularly around the abdomen, is itself a source of inflammatory signaling, so that fat tissue actively contributes to the smoldering background inflammation that keeps wounds stuck. Poor sleep raises inflammatory markers and degrades immune coordination, while good sleep is when much of the body's repair and immune regulation actually occurs. Chronic stress, through the hormone cortisol, directly suppresses the immune response and the inflammatory resolution a wound needs, and prolonged high cortisol is a well-documented impairer of wound healing. These are not soft suggestions. They are inputs into the exact molecular systems we have spent this whole account describing: the macrophage switch, the inflammatory signaling, the oxygen delivery, the collagen synthesis. The mechanisms tell you precisely why these things matter, and that is the entire value of understanding them. You are not following arbitrary health advice. You are removing specific breaks from specific machinery. Step back now and look at the whole picture, the full arc of what happens when that steel edge slides through your skin at 65 instead of 8. The clot still forms in minutes, the platelets still pour out their growth factors. The ancient cascade still runs exactly as it did when you were a child, because that machinery does not age much at all. But the crews that answer the call have changed. The construction crew is smaller. Because so many fibroblasts have spent their 50 divisions and gone silent, their telomeres worn down to the nub, and the ones still working build less collagen and tear down more on a skin whose underlying structure has flattened and thinned. The cleanup crew arrives a little disorganized, its first responders firing wide, its macrophages stuck in attack mode, refusing to make the switch to repair, while the whole body simmers in a low-grade inflammation stoked by senescent cells that will not die and will not stop sounding the alarm. And the supply lines that every crew depends on have narrowed, the arteries stiffened, the capillaries fewer and slower to regrow, the nitric oxide that would open them mopped up by the very inflammation that will not quit, so that oxygen, the fuel, and the raw material both, arrives in short supply, and without it, the collagen comes out weak and the loop tightens on itself. 3 crews, 1 web, every delay feeding every other. But woven through all of it is the line between what you cannot change and what you can, and that line is where this stops being a story about decline and becomes a story about agency. You cannot make your cells young, but you can keep your blood moving, your sugar steady, your blood pressure controlled, the smoke out of your lungs, the protein and the vitamin C and the zinc on your plate, the weight off your middle, the sleep in your nights, and the stress out of your days, and every one of those acts directly on the machinery we have traced, opening the supply lines, calming the inflammation, feeding the builders. The wound on the back of your hand will never close in a week again, that much is honest. But the difference between a wound that heals reasonably and one that drags on for months is, to a remarkable degree, sitting in your own hands, written in the same chemistry that built the clot in the first place. Your body has been repairing itself, flawlessly and without your attention, since before you could walk. It is still trying to do exactly that, every single time you are cut. The crews are older now, and they are slower, but they still report for duty the moment the alarm sounds, and the least you can do is make sure the supplies are waiting for them when they arrive.